All right, so good afternoon, all. Welcome to the tutorials and live discussions on week 7 topics regarding the course Wheel Mobile Robots. So basically, we have 0 attendance for today's session. So anyway, like if people are not, the time is not convenient for them, they can always find a recorded version of this lecture in the course website itself, so that they can go back and visit. They can go back to the course and they can revisit whatever topics and questions that we have discussed in today's session. So the main motive of this session, or the intent of today's session, is to discuss some sample problems regarding week 7 topics, which are mostly related to motion control of mobile robots. Motion control of mobile robots. And during the first 2 introductory lectures, we have seen different classification of motion controls, whether it is a set point control, whether it is a tracking control, what's the difference between a kinematic control, difference between kinematic control and dynamic control, feed forward control and feedback control. All these sort of things we have seen in the first 2 introductory lectures. And in the subsequent lectures, we have also visited simulation of various types of controllers, including kinematic controls as well as dynamic controls. We have also seen an example of a backstepping or a cascaded control aspect. So, yeah, with that, like we'll just go forward with the sessions actually, which is about solving tutorial questions regarding, motion control of mobile robots. So here goes. Question 1 basically asks, a robot is not only a mechanical architecture, but is also slaved by dash that impacts its performance. So it's a fairly straightforward question. It says a robot is not only mechanical architecture, but is also slave. It's basically, keyword to look for is slaved action by something that impacts its performance. So multiple options, 6 options are given for as a multiple choice question. The first option is sensor, second option is controller, third option is planner, fourth option is an actuator, fifth option is a navigator, and sixth is a supporter. So the question is about something that basically slaves a robot. So if you typically look at the control diagram, a simple feedback control diagram of any system, it doesn't have to be a robotic system. It'll look something like this. Basically have a controller. Then from the controller will basically compute a signal. It will basically go to plant. Plant will give you some output basically. And right. So basically, this is basically a simple representation of a system, basically a system that is controlled by a controller using feedback, using its system feedback. So over here we have a plant. So the plant basically has some Over here we have a controller, and the controller basically controls the actuators, so that the plant would do its corresponding operations. And using some sensors, whatever parameters the plant is outputting, we'll measure it using sensors. And it is again feedback to the controller, where what we give as feedback to the controller will be the difference between our desired parameters and the output parameters, desired and output parameters. Whatever difference that we are getting between desired parameters and output parameters, we are feeding it back to the controller. And based on the signal it is receiving, the controller would give it appropriate control signals to the plant. So the cycle basically goes. So a simple answer would be it can be easily seen that the plant is basically slaved by a controller. So all the things that the plant is supposed to do, or whatever the plant can do, is basically controlled by the controller based on the signal it receives. So in case of a robotic system, we are controlling a robotic system in terms of dynamic level. We'll have a robot over here. It'll have its own actuators and sensors. And if you're trying to control the robot on dynamic level, the controller would compute the output torque. The torque to actuate its actuator so that it will basically follow the desired trajectory. So the output would be eta, the trajectory, and the input would be our desired trajectory. So the difference between desired and output trajectory, that would be eta tilde, that would be fed into the controller, and based on whatever algorithm that we are using within the controller, it will basically give you back the control torque. So again, like in that regard, the correct answer would be something that, it asks about something that is slaved by something, basically. Exactly. In that regard, the correct answer would be controller, because no other option makes sense. Because a robot is basically slaved by the controller. So I hope we don't have any conflict in that. It's a fairly straightforward question. It's basically it's kind of a definition. So if you check the answer is indeed controller. So please let me know if you have any questions, or if there is any clarity issues, or if my audio visual is not clear, or in case my screen is not clear, or if there is any kind of lag, please, you can feel free to interrupt the session, and please let me know. Yeah. So regarding question 2, it says a seamless integration of inaccurate models and limiting sensing capabilities is known as, right? Seamless integration of, like, so this is the definition of what exactly out of these given choices? Is it the definition of classical robotics, or is it the definition of probabilistic robotics, modern robotics, hybrid robotics, soft robotics, or field robotics? Excuse me. Again, this is basically a definition kind of question. Like, the answer is fairly straightforward. So if I recall a slide from the lectures from Dr. Shantakumar, I hope you can recall the slide. These are basically from the introductory slides from week 7 courses. So again, when we discuss the trends of robotics during various decades, we have discussed classical robotics, we have discussed reactive paradigm, we have discussed hybrid paradigms, we have also discussed probabilistic robotics, and we have also discussed learning-based robotics. So the answer is right here, right? The seamless integration of models and sensing. So we'll have to work with inaccurate models, because whatever we develop, like the model we try and develop for a robotic system, be it a kinematic model or a dynamic model, it might not be exact, because we cannot accurately predict how a robot behaves virtually. So we'll have to realize that we'll only have inaccurate models. However accurately we try to model, there will be some inaccuracies in our model. And sensors are also not foolproof. Like there are some sensor errors associated with them. So again, this is basically a definition kind of question. So for the question that asks, the question exactly asks this point. It says the seamless integration of models and sensing. That is exactly what the question says. So in that regard, the answer is probabilistic robots. Right. So seamless integration of inaccurate models and limited sensing capabilities is known as probabilistic robots. So for the sake of completeness, we'll basically review through the rest of the paradigms, because it might come useful in during the further part of this session. So in classical robotics, that was popular during mid-70s, 1970s. They never had any sensors actually. They didn't play with sensors. They actually played with models, whether it is kinematic models or dynamic models, dynamics. It doesn't require any sensors. So whatever input that we are giving to the robots actuators, that is derived purely from the models, dynamic or kinematic models. So it doesn't have any feedback. It's purely based on a feed-forward kind of an. And during mid-70s, they actually went quite the opposite way. They didn't bother with the kinematic and dynamic models. Rather than that, they relied only on sensors, because they relied on a feedback, and they never incorporated any aspect from the models. They only relied on sensing. So if we have a desired parameter, if we want the robot to follow a desired trajectory, right, and the robot is giving you an actual trajectory, there will be some differences between this desired and actual, right? So the feedback from the robot is basically taken back, so that it can be compared with this desired. So the difference between desired and the actual trajectories, the difference between desired and actual is basically considered, so that further inputs can be given to the robot. So again, if I go back and go back to the first question, I have basically drawn a control loop actually. So we have a actual output from the robotic system. We also have a desired parameters, and we also have an output parameters. So whatever we are getting from the robot, we are taking it as a feedback, right? And we are comparing that the error between the desired and the actual parameters is basically taken care of by the controller, so that it can give appropriate control signals to the robot. But in case of a reactive paradigm, whatever is happening on the controller, it does not depend on models. It only depends on the feedback. It only depends on the sensors. I hope that is clear, because what I mean when by model is that, like in case of a kinematic model, eta dot would be j of psi into theta. This is what we have in terms of kinematics. And in terms of dynamics, tau would be d of zeta dot plus n of zeta. This is kinematics, and this is dynamics. Right? These are purely model-based controls, right? But in case of a model that does not have any model, it will look something like this. Tau would be Kp eta tilde plus Kd eta tilde. It does not have any components from the model. It only has the difference between actual and desired, where eta tilde is desired trajectory minus actual trajectory. So this is an example of a PD control, right? This is basically an example of PD control, and no component of the model comes into play in PD control. It's purely a feedback based or a reactive based. And during the 90s, it evolved further, and basically we have a hybrid scheme. So it will have a model based at higher levels and a reactive at lower levels. Like higher levels and lower levels, it basically means like if you are using this cascaded control, as you might have already seen in the lectures, it uses kinematic control at the outer loop or at a higher level, and it uses dynamic control at a lower level. So again, like it's basically a combination of classical robotics that is purely based on models, and the reactive paradigm that relies on sensors also. So you might have come across the term called the computed torque control or computed velocity control. So it will have components from the model, like it will have components from the model, as well as it will also have components from the sensors also. It will have a feed forward term plus a feed feedback term also. We'll see that later also. And in probabilistic robots, again, like it talks about the seamless integration of models and sensing. So whatever we are sensing, like not everything cannot be modeled. So some things should be incorporated into the model using sensors actually. So that should be also there. And yeah, we should also be aware of the inaccuracies in our models actually. So these all can be modeled using probabilities, like the errors in sensors. Like it's basically in the form of a Gaussian distribution. So all these things will be taken care of in probabilistic robots. And recently, since 2015, we also have learning based, like data-driven, deep learning based robotic motion control systems. Yeah. So again, like moving on. So for the given question, the correct answer is probabilistic robots. It's all right. Again. So moving on to question 3, it says the inverse differential kinematics or inverse dynamics is equal to, can anyone say the correct answer? The inverse differential kinematics or inverse dynamics is equal to a feedback or closed loop control. Is it a feed forward or an open loop control? Is it a motion based control? Is it a robust control, an adaptive control, or an optimal control? So again, like I'll write the basic control law of this inverse differential kinematics as well as inverse dynamics control. So inverse differential kinematics would mean eta desired dot would be j of psi theta, and zeta is the control input basically. This is basically the control input. And this is the desired trajectory. So based on the inverse differential kinematics, the controller would be zeta would be j of psi inverse eta desired dot. So yeah, this is basically inverse kinematics, inverse differential kinematics. And what about inverse dynamics? That is simply tau would be e of theta, theta desired dot plus n of theta. This is inverse dynamics. So the question says whether is it a feedback, like it applies to both of these control laws, right? It says or, so it applies to both of these control laws. It says whether it is a feedback or a closed loop control, whether it is a feed forward or open loop control. Is it a motion based control, a robust control, an adaptive control, or optimal control? So given these are the control laws, could anyone of you answer the question?
Feed forward open loop controls.
Exactly, yeah. This is basically a feed forward or an open loop control. Because there is no feedback term, right? We only have a feed forward term. There is no feedback term. Feedback term means, like, again, I'll reproduce the controller law actually. Controller, we'll have a robot. Right. Desired. And based on whatever control law we are using, I am assuming we are using the dynamic control. So if we are giving eta desired as input, and the controller would give you the torque, the torque computed based on this input. This thing. Controller will basically compute the torque based on this equation. This is coming from the controller. It gives the torque. It will basically actuate the actuators of the robot, and the robot will execute some motion eta. This is actual trajectory. So this is all what this controller basically says. Because there is no feedback term. We are not taking any feedback from the actual trajectory. Right. There is no feedback. It's just a feed forward. So in that regard, the correct answer is a feed forward or an open loop control, because it's definitely not a feedback law, or it's not a closed loop law. It's not a motion based control. It's not a robust control. It's not an adaptive control. It's also not an optimal control. Right? So I hope we don't have any further questions in that. The answer is indeed it's a feed forward or a open loop control. Yeah. So yeah, moving on to question 4. It says a robust control aims at controlling with a small error a class of robotic manipulators whose model is not accurately known with the same control. Again, this question is kind of a definition of what we have seen during the lectures. So I'm recalling the definitions from the lecture itself. So it basically gives the definition of robust controllers. Like in the lectures, sir has also given some examples of robust control also. So it says robust control aims at controlling with a small error a class of robotic manipulators whose model is not accurately known with the same controller. So we always write the model of a robot as tau would be d of theta dot plus n of theta. So again, like we cannot be 100% sure that this would exactly model a robot, because there may be some other terms also. There may be some terms due to the friction in the robot. We are not taking that into consideration, friction terms. And maybe due to some terms due to actuator saturation. Lot of other terms could come, and whatever we have estimated as this mass matrix, it might not be even 100% accurate. There could be some differences also, because we cannot exactly 100% determine how the mass matrix would look like in case of a real system. So again, robust control says aims at controlling with a small error a class of robotic manipulators model is not accurately known with the same control. Whereas in case of an adaptive control, it deals with uncertainty in system parameters, and it requires precise knowledge of the structure of the system. Both are basically a bit different. And the question basically asks the definition of, it says robust control aims at controlling with a small error a class of robotic manipulators. Model is not accurately the same. So again, like we have already seen the definition. So according to the definitions, this is basically right. So like we might not even know the model accurately. There could be some discrepancies, but still, like we can still control the robotic system with a slight error, even if the entire model is not fully known. But in case of adaptive control, like we need to know the structure of the robot, even if there are some uncertainties. We still need to know the entire structure of the robot, right? Like if this is how the dynamic model looks like, theta dot plus n of theta plus some frictional values. Then in case of this actual robotic system, it would be some d actual theta dot plus n actual theta plus fp actual. So this is what we estimate, and this is the actual parameters of the robotic system. We'll never know for sure, but the structure should be exact in case of adaptive control. Based on the definition itself, it says, the correct answer would be the given statement is indeed a definition of the robust control. Yeah, so the answer is indeed true. Again, the question is regarding stability or asymptotic stability. So asymptotically stable means, like, what is the basic definition of asymptotically stable? So when time tends to infinity, the tracking errors tend to infinity. So tracking errors or eta tilde. This is what we use throughout the lectures, tilde, tracking errors. That is basically the difference between desired trajectory and actual trajectory. Desired is what we want the robot to move, the trajectory that we want the robot to move, and actual trajectory is the exact trajectory that the robot is trying to. There will be always some difference between exact and the desired trajectory because of the external disturbances, uncertainty in models, all those different things. All right. So it says, the first option says, as time tends to infinity, tracking errors tends to infinity. So is that true or false? And the second option says, first option says time tends to infinity, tilde tends to infinity. And the second option says when time tends to infinity, eta tilde tend to be bounded. Bounded in the sense like there will be still some error, but it won't go beyond the bound. So if I'm treating this ball as a bound, so as if the eta tilde, yeah. So this is the initial condition of eta tilde. It starts from an initial configuration, and as time tends to 0, it basically evolves within the ball. But as time tends to infinity, it will settle somewhere within the ball, but it won't go outside the ball. That's what the second statement says. It won't go outside. It can settle anywhere within this ball, within this boundary, but it won't go beyond. And option 3 states when the time tends to infinity, the tracking errors tend to 0. Time tends to infinity, eta tilde tend to 0. And when time tends, fourth option says when time tends to 0, the tracking errors tend to time tend to 0. Tracking errors tend to infinity. Fifth option says time tends to 0. Tracking errors tend to 0. Sixth option says time tends to 0. Tracking errors are bounded. So which of the option is the correct? Sorry, yeah. Is model and structure used in the same context? I didn't see that question earlier, really. No, it might not. It's not exactly same. Actually, it's not same. Like structure means like again, like I've told you earlier. Like in this case, the structure is more or less the same, right? It is more or less the same. Like the estimated model or the estimated model will still have some frictional. Some sort of frictional parameters. So most often what we do is that we would, in order to model the friction, we would simply give this as some coefficient of this vector, n of theta, the other effects vector. So we would take the friction to be proportional to the velocity of the robot. So we would simply give it as 0.3 times what is the velocity? This vector zeta, right? This is the velocity. So this is how we would usually model friction. Usually model or give a brief estimate of friction in terms of robotic system. But in case of actual, it would be something different. But still, like we have some sort of uncertain estimate of the friction. So in that regard, that is basically conforming with the structure. Right? But in case of model, like we might not even require this thing in terms of a model. Like model can be, see, in this case, like both of them are not conformed. It basically has a different structure. It basically have a different structure actually. Right? Both of these models, tau and tau actually, both of these models have different structure. It does not even conform to the actual system. If you are using a purely if you are using a purely feedback system without any model, it will look something like Kp eta tilde plus Kd eta. So basically, the actual and the input, the controller input, and how the actual dynamics would behave in case of a robot is entirely of different structure. Right? Even though it have different models, yeah, as of now it has different models and different structures as well. I hope this is clear actually, right? Yeah. Okay, so again, question 5. What would be the correct answer in this regard? Asymptotically stable. So I think we might have come across what asymptotically stable. So if we have an error, a time versus error plot, what asymptotically stable means, like error will basically begin from a non-zero value. It can also begin from a zero value if the initial trajectory, initial condition of the desired and actual trajectories are basically zero. But consider we are beginning from a case where the initial and actual conditions are non-zero. So as time tends to infinity, our the error basically asymptotically tend to zero as time goes to infinity. So that is basically a definition of asymptotic stability. As time tend to infinity, the errors, the tracking errors basically tend to zero. Whereas in case of bounded errors, unbounded errors, and all these things, like it won't tend to zero, but it will stay within a bound. Actually, there will be a minimal bound and a maximal bound. It will stay within a bound. But in case of asymptotic stability, irrespective of where we begin, irrespective of the initial condition, as time tend to infinity, the errors will tend to zero. But in case of bounded errors, it basically depends on the initial condition. So if you are beginning from some other initial conditions, it may go out of the bound. If you are beginning within a region, it will stay within the region. That is how this bounded errors basically work. But asymptotic stability doesn't matter. Wherever you start, you can start from any initial condition. As time tend to infinity, it will asymptotically, the tracking errors would converge asymptotically to zero. In that regard, the correct option is option 3. Yeah. So again, question 6, it says, in a set point or a regulatory position control, the desired position vectors and velocity vectors are continuous. So the keyword to take care into your consideration is set point or regulatory position control. So again, you might have come across these terms. We have a different classification of controls, set point controls. We also have a trajectory control. Right. So the definition is fairly self-explanatory, because if I recall from the lectures, snap from the lectures, so set point control basically deals with point-to-point motion. It does not deal with how you reach from one point, does not deal with how you reach from this point to this final point. The only thing that matters is the initial configuration and the final configuration. It does not matter how you traverse this path. It could be any path actually. The time dependence is not a point of concern. Right. So we'll give an initial position and we'll give a final position. And velocity, since we are not tracking, well, we can't give velocity as a function of time. Well, it's basically zero. In most cases, velocity is considered as zero. We'll give an initial time, initial position, and the final position. But in case of a tracking problem, so how the robot moves from the initial configuration to the final configuration at every instant of time is a matter of concern. So we would want to control the robot so that it will go through a desired trajectory at every instant of time. Right. So in that regard, tracking control basically tracks the robot's position, velocities, and accelerations as functions of. So in this regard, a set point control or a regulatory position control, the desired position vectors and velocity vectors are continuous. That is a false statement, because these are not continuous functions of time. For set point control, these cannot be continuous functions of time. Right? The velocities and accelerations are essentially zero. So again, like the basically it's basically kind of a definition kind of a question. Like set point control does not have the second order, first order and second order derivatives of position. So in that regard, it cannot be continuous. The position vectors and velocity vectors cannot be continuous. So in that regard, the correct answer is option 2, false. So I hope we don't have any questions in that regard. Okay. And the question 7 says the second order dynamics is stable as per the following criterion. So eta tilde double dot plus lambda 1 eta tilde plus lambda 2 eta tilde equal to 0. So again, like you might have come across lot of second order systems. So it's similar to this thing, a spring mass damper system. Mx double dot plus px dot plus kx equal to 0. Right? So like, or any second order system, like I'll take in case of a generic second order system, right? X double dot plus lambda 1 x dot plus lambda 2 x equal to 0. So we also know the homogeneous solution of a generic second order system. So in case of a second order linear ordinary differential equation, the solution would look something like this. It will always have a general form, the homogeneous solution. That will be of this form: C1 e raised to S1t plus C2 e raised to S2. This is how a second order system's response would look like if we solve the system. Right? And C1 and C2 are basically arbitrary constants that depends on the initial condition, and S1 and S2 are basically depend on the system parameters. And how do you calculate this S1 and S2? S1 and S2 is basically when by solving this quadratic equation, S1 comma 2 minus b plus or minus b square minus 4 is a similar thing, minus lambda 1 plus or minus root of lambda 1 square minus 4 lambda 1 lambda 2 the whole divided by 2. Right? So if we want this entire thing to be stable, right? If we want this system to be stable, so stability means the error should be bounded. So as time tends to 0, time tends to infinity, this eta tilde should tend to 0. Right? So again, like I have used here to demonstrate a general case, but in case of x, we would have this eta tilde. Right? So if we come back to a specific case, so this is basically a differential equation in terms of eta tilde double dot plus capital lambda 1 eta tilde dot plus lambda 2 eta tilde. This would be equal to 0. And if we want the system to be stable, stable means as time tends to infinity, eta tilde would tend to 0. And the response eta tilde of time would look something like C1 e raised to S1t plus C2 e raised to S2. And the possible way of making this solution to converge to 0 as time tends to infinity is to make S1 and S2 negative. The roots has to be negative. Then only as time tends to infinity, it will be like C1 e raised to minus S1t and C2 e raised to minus S2t. So like it is something exponential e raised to minus infinity. As time tends to infinity, the term would be like e raised to minus infinity. So both of these terms would basically converge to 0. So depending on which one is larger, see whether it is S1 or S2, which one is larger. So I'll basically give you an example. So consider this system, y double dot plus 5y dot plus 6y. This is equal to 0. So what are the roots of this solution, this differential equation? S12 would be minus 5 plus or minus root of 25 minus 4 into 6 the whole divided by. And the roots are, I suppose, minus 3 and minus 2. So the response of the system, if the independent variable is t, is y of t would be c1 e raised to minus 2t plus c2 e raised to minus. So for a system like this, it is guaranteed that as time tend to infinity, y of t tend to 0. And look at the coefficients of this differential equation, right? The coefficients are all positive. These are all positive. So if you can correlate this thing to the question that is asked. So we have a differential equation, eta tilde double dot plus lambda 1 eta tilde dot plus lambda 2 eta tilde. And what should be the condition of lambda 1 and lambda 2 so that the error dynamics would be stable as time tend to infinity. So I hope the evidence that I have provided you is sufficient. I'm straight away jumping on to the answer. The answer is option 3. Right? Lambda 1 should be greater than 0, lambda 2 should be greater than 0. So otherwise, there could be case of undamped system. It could also be like if something happens and if these roots are positive, as time tends to infinity, it could exponentially blow up also. It might not be stable. And sometimes it might not even dampen out also. It could be undamped system also. So I hope whatever evidence or whatever example I have provided is sufficient. So the condition should be, the error dynamics should be of the following: eta tilde double dot plus lambda 1 eta tilde plus lambda 2 eta tilde should be 0, and lambda 1 and lambda 2 should be greater than 0. If that condition is followed, then the second order dynamics stable. So again, I hope that is sufficient, right? So please let me know if you have any conflict regarding this question or any of the questions that we are discussing. Okay. So question 8, it says it's regarding computed velocity control. So it says the vector of input commands or control inputs of a computed velocity control is given as. So which of these following options corresponds to computed velocity control? Computed velocity control, right? So again, like I'll briefly dish out the objectives actually. So again, like we want the system to follow a first order error dynamics. Like we want the system to behave. I'll write it over here. So we want the system to behave as per eta tilde dot plus lambda of eta tilde equal to 0. So for a kinematic control, we would want the system to behave or respond as per the first order error dynamic. So again, this is also first order differential equation, right? So what will be the homogeneous solution of this equation, right? So if time is the independent variable, eta tilde of time would be c1 e raised to lambda t, right? So this is how we would want the system to behave, or in this case, it won't be this lambda. There will be some, there will be some minus st. This is how the system would behave, and we would want the system to behave like this as per this differential equation, so that as time tend to infinity, eta tilde would tend to 0. So the solution for this differential equation is this one. So from solution, it can be fairly seen that as time tend to infinity, the error or the tracking error would tend to 0 from this equation. It's fairly evident. So again, going back to this differential equation. What is this eta tilde again? Eta tilde is again eta desired minus eta. That is the difference between the desired trajectory and the actual trajectory. Right. So I'm rewriting equation 1. I'm rewriting this equation 1 as follows. I'm substituting this relation. Right. So what's the space? Eta desired dot minus eta dot plus lambda eta tilde. This is 0. And I'm bringing this eta tilde eta dot to the other side of this equation. Eta will be eta dot. And from this kinematics, what is this eta dot? So from kinematics, eta dot is j of psi times zeta. And zeta is basically the control input that we are giving onto the robot. This is basically the control input. And our question is basically to find the velocity input command or the control input. This is what the question basically seeks. So we need to find the relation between the control input zeta and the feedback terms actually. Right. So if I'm substituting this relation onto this equation, right? If I'm labeling this as equation 2 and if I'm labeling this as equation 3. So substituting 3 back in equation 2 would yield you eta desired dot plus lambda eta tilde should be equal to j of psi zeta. Then what would be zeta? Then zeta, the control input, zeta would be j of zeta inverse eta desired dot plus lambda eta tilde. So if we basically give this onto a robotic system, if we give this control input to a robotic system, it would behave as per this differential equation. And what is the solution of this differential equation? This is the solution of that differential equation. Whereas time tend to infinity, the tracking errors would tend to 0. That is exactly what we want. And this is how the control input would look like. So we have a feed forward term over here, feed forward. And we also have a feedback term. Feedback term. It consists of both the feed forward term. This is the desired trajectory that will go into the controller, and the feedback term. That is basically the difference between the feed forward term and the actual trajectory that the robot is executing. So again, I hope the reasoning is clear enough. So in that regard, what would be the correct option? So in that regard, option A, B, C, I think option D is the correct option. That matches with our answer over here. Right? Yeah. Okay. Yeah. All right. So yeah, moving on to the second question, question number 9. This is also similar to the previous question, but in the dynamic level. Right? Earlier, we only considered first order aerodynamics because the entire model that we worked was just the velocity, was just the kinematic model. And here, we are basically developing the robot in dynamics as well. We are developing the dynamics of the robot as well. So we need to ensure that, like, yeah, the question, I'll briefly go through the question. It says the computed input control of a land-based robot can be given as. So which of these following options is the correct answer? Right. So I'll go through this slowly. Actually, I'll go through the derivation slowly. So what are our requirements? Like we want the robot to move through a desired trajectory that is defined in terms of a position vector, its velocity vector, theta dot of t, and an acceleration vector. So these are how we want the robot to move. Actually, these are the desired trajectories of the robot, and our objective is okay. We are also defining this eta tilde as well. Eta tilde is basically the difference between desired trajectory and actual trajectory. All right, and our objective is as time tend to infinity, the tracking errors in position and velocities, eta tilde and eta tilde to tend to 0. So again, like I think a few questions before we have seen this differential equation, right? Eta tilde double dot plus some, I'll call this thing KD eta tilde dot plus KP eta tilde. A few questions ago, we have seen this differential equation. And if we choose KP and KP, provided KP and KD are greater than 0, the dynamics of or the response of the system would look something like this. Eta tilde of t would be C1 e raised to S1t plus C2 e raised to S2. So if we judiciously select KP and KD, or if we choose KP and KD greater than 0, the solution or the homogeneous solution of this differential equation would follow. The solution is basically this equation. And as time tend to infinity, it's fairly straightforward to see that eta and eta tilde dot tend to 0 basically for this corresponding differential equation. And this is how we want the robotic system to behave as in that regard. All right, so this is basically our objective. We want the robotic system to behave as per this differential equation. And based on how we choose this KP and KD, the solution would look something like this. And mind, don't be fooled by the coefficients of this S1 and S2. If we choose KP and KD greater than 0, S1 and S2 would turn out to be negative. This would turn out, there will be a negative term in this. The solutions would also always be negative. So as time tend to infinity, this entire eta tilde of t would tend to 0. Right. Okay, yeah. So in this differential equation, I'm labeling this as equation 1. So yeah, equation 1 implies eta tilde double dot plus KD eta tilde dot plus KP eta tilde equal to 0. And I'm rewriting this eta tilde in terms of eta desired and eta. All right. Okay, so it'll indeed turn out to be like eta desired double dot minus eta double dot plus KD eta tilde dot plus KP eta tilde equal to 0. And I'm bringing this this term. The procedure is exactly similar to what we did during the previous question during the computed velocity control. I'm bringing this eta tilde dot to the other side of this equation. So it looks something like this would be eta double dot, right? So we'll leave this equation here for the time being. This one is equation number 2. Okay, I'm reproducing some equations from robot dynamics. So robot dynamics basically says the torque of the robot is equal to the mass matrix d of zeta desired plus n of zeta desired. Right. I'll label this as equation number 3. Right. And from robot kinematics, eta desired dot would be j of psi zeta desired. So again, like, how can we work with this equation? Equation 3 and equation. So as per robot dynamics, this is the torque vector tau would be d of zeta desired plus n of zeta desired. And as per the robot kinematics, eta dot would be j of psi times zeta desired. Yeah. And if I'm further differentiating this equation, the robot kinematics equation, how would it look like? Like, for the time being, forget the subscript d, forget it, everything in terms of desired. I'm writing generally actually. So I'm differentiating the robot kinematics. It will be like eta desired double dot would be, I'm using the chain rule, j of psi dot zeta desired dot plus j of psi. Sorry, there is no dot over here. J of psi zeta desired dot. Right? I'm labeling this as equation number 5. And there is a dot over here also. I forgot to mention that. There's a dot over here because this is acceleration, right? So there is a dot. So yeah, how would we get back actually? So substituting equations, this 3 and equation 5 back onto this equation 2. How would it look like? It look like eta desired double dot plus kd eta tilde dot plus kp eta tilde. This would be equal to eta desired can be obtained from this equation, right? Equation number 5. I'm writing that for the time being. Eta double dot j dot of psi j dot of psi zeta desired plus j, sorry, I think be like j dot of psi zeta desired plus, and instead of this zeta desired dot, I'm substituting this equation from this equation. It would be like tau minus n of zeta the whole pre-multiplied by d inverse. Right? Is it correct? There is also another term I think I have missed. I'll rewrite this again. So again, substituting equations 5 and 3 on equations 2. This would yield eta desired double dot plus kd eta tilde dot plus kp eta tilde. This would be equal to j dot of psi zeta desired plus it would be j of psi d inverse tau minus n of zeta. And from this equation, I'm calling this equation 6. If this is equation 6, our objective is to find the control input. Right. So rearranging this thing, it would be like to find out tau, it would be yeah. I'm bringing each and everything over to the other side. First, I'm bringing this term to this side. Right? So it will be like eta desired double dot minus j dot of psi zeta desired. Then you also have a kp eta tilde plus kd, right? Kd eta tilde dot plus kp eta tilde. Then you have to pre-multiply it first with j of psi zeta inverse. Then comes a d also. So d inverse, if you take this d inverse over to the other side, it will be. Then the remaining term would be this n of zeta. Right. So this is what your control input tau would look like. So this entire term would be d matrix multiplied by j matrix with j of psi, the whole inverse, and within the brackets we have a feed forward term eta desired double dot minus j dot of psi zeta desired plus kd eta tilde dot plus kp. These are the feedback terms actually. These two are basically the feedback terms. These are the feed forward terms. And usually we would ignore this term, this j dot of psi zeta, because these are mostly 0. And we also have a feedback linearization term. This is what we would give as a torque input to the control. So this is basically the essence of computed torque control. So on going back to the question, which is the most, yeah, I'll reproduce this entire thing back to the previous one. So the option that is most in line with what we have derived so far is it option 1? I don't think so, because the acceleration vector is only pre-multiplied by this D matrix. We also have a J inverse matrix. It's not even option 2. Option 3 also. Option 3 looks likely. Yeah, option 3 looks quite likely. Option 4 doesn't look likely. Option 3, does it look likely? I don't think so, because I don't think we have this term, right? Yeah, essentially j dot of psi into zeta desired. The term over here, right? J dot of psi zeta desired dot. They have zeta desired. They have further simplified this thing as. They have again further applied this inverse transformation j dot of psi, j of psi, zeta desired dot. They have made this transformation actually. Instead of the zeta, they have made this transformation. And that is what they have applied in these equations as well. Sorry, I think this is j of psi inverse, right? Yeah. And out of all these options, which one would be the correct answer? I think options. Yeah, option C looks more likely, right? Rather than option B doesn't look likely because it doesn't have a D matrix. And what about option A, B, C, D? That also doesn't look likely. To my eyes, both look essentially identical, right? So I think in that regard, the right option is, you go and check the answer key is option C. Or yeah, option C is indeed correct, because this term, this feedback linearization term, is basically missing in this term, in this equation. In that regard, option 3 is indeed correct, because that is more or less in line with what we have derived. All the terms are basically matching with the derivation that we have just seen right now. Yeah, and option 10, question 10 is basically again a description kind of a question. It says, motion control is a subfield of dash encompassing the systems or subsystems involving in moving parts of machine in the control manner. Like, is it machines? Is it kinematics? Is it processing? Is it navigation, automation, and account? Right. So I hope we can all agree that the most appropriate answer is automation. This regard, right? Because motion control is basically an essential component in automation. It involves subsystems or systems or subsystems involving several moving parts of machines in a controlled manner. So motion control is not a subsystem of machines. Machines itself, machines and mechanism. Machines, definition of machines is something that is used to transfer forces from one link to the other. That's all what a machine means. Kinematics does not bring any forces into a picture. Processing is a generic term. Navigation is also not applicable to this. Automation is only the option that makes real sense. Accounting is also not applicable in this context. So I hope we don't have any further conflict in this regard. Automation itself is the correct answer. Yeah. And question 11 says, what is or are the primary or important control objectives? Important control objectives. Primary, it says primary actually. So all of these might be control objectives, but it says which are the primary control objectives. Is it the tracking performance? Is it the resource optimization? Is it the time optimization? Is it stability? Error minimization, regulation? So I guess like more or less all of these are basically objectives of control actually. But it doesn't matter, like if the system is not stable, like if the errors goes out of bound as time progresses. So irrespective of how the controller fares in tracking or optimization or error minimization or regulation, it doesn't matter because the system is bound to blow up. Like if it is not stable, then whatever it does in other aspect does not matter. So that regard, the primary control objective of any control system should be and is always going to be stability of the system. We always have to ensure that the controller that we are designed is always going to be stable. So in that regard, the primary control objective is indeed stability. Right? Yeah. And yeah, moving on to question 12. It says something is the change of state at any instant of time of a body. It only states the change of state. Yeah. So first statement state statement 1 says it's only about change of state. Right. And what about the second statement? It says something is the state of a body or bodies over a period of time. Right. Statement. It's state of body over a period of time. So at each and every instant of time, we would have the state of the body, what orientation the body is, what position the body is at every instant. And for statement 3, what does it say? It says something is the position of the body over a period of time without worrying of velocity or higher order terms. Right? So we are not worrying about state of body over a period of time without considering velocities and accelerations. So if you take a look at this answer, the correct answer would be a combination of motion, trajectory, and path. Right. So statement 1 says it's only about a change of state of a robot from one state to another state. Doesn't matter how the robot reaches from one state to the other. We don't need to know we don't need to know at every instant of time what are the transitioning states. We only need to know the initial and the final states. In that regard, that is the definition, the clear-cut definition of motion. Right, from one state to another. And regarding statement 2, it says the state of body over a period of time. So we'll have an initial condition. We'll also have a desired final position, and we'll also have to satisfy our desired trajectory as well. Trajectory would be defined in terms of velocity with respect to time and acceleration with respect to time. And the second statement basically states the state of body or bodies over a period of time. So in that regard, the trajectory comes into play, the time derivative of the position, which is velocity, and its derivative acceleration. So at every instant of time, we need to know the trajectory of the body. So in that regard, the correct choice is trajectory. And for the third state, we would still know the positions of the over a period of time. We would still know the position of the body, but we are not considered about the velocities or higher order terms. We are not considered about. We would still know the position. That's all. Position as a function of time, and nothing more in that regard. We don't bother about accelerations or velocities. In case of a car parking problem, it would take a desired stages of maneuvers for a car to reach from the starting point to the initial point. Again, we are not really bothered about the velocity or acceleration at each and every point, each and every instant of time. We are only bothered about the path the vehicle takes so that it can successfully park from the initial starting position to the final. Right. So again, I think I made a mistake. The second statement is corresponding to the trajectory, and the third option is corresponding to the path. Path would mean simply the information about the position alone without giving any regards to velocities and accelerations. So in that regard, the correct combination would be motion, trajectory, and path. Option A is the right answer. Right. So again, we'll look at a few more questions that is basically from the tutorial, basically from the current tutorial, current assignments of the course that is currently running. So since the deadline of the assignments is over, we can discuss the solutions over here. So again, these are more or less similar to the questions that we have already discussed. Right. So you might have already seen a similar question. So which of the following are open loop control laws for land-based wheel mobile robots? So I'll simply go through the answer. I have already given you the justification. Inverse differential kinematics is basically an open loop control. Right? Computed velocity control it is a closed loop control because it will have a feed forward term. It will also have a feedback term as well. And PID control is purely feedback. And inverse dynamics is also open loop. So we'll just compute the required torque based on the desired trajectory alone. That is, tau would be E of zeta desired dot plus N of zeta desired. There are no feedback terms in it. So we'll compute the torque that we are supposed to give onto the robot purely based on the desired trajectory. That's all. There are no feedback terms. Computer torque control, again similar to the computer velocity control. It's again a closed loop control. We also again have feed forward and feedback terms. Cascaded or backstepping control, again it also has a feed forward and feedback term. This is also a closed loop. So in this regard, this option has multiple correct answers. The question says to identify open loop controllers. So inverse differential kinematics and inverse dynamics, both of these are basically open loop or feed forward controllers, right? So the options A and options. And moving on to question 14. It says to identify the incorrect statements. So model-free control relies on pure on sensing feedback only. Model-free, right? This is basically a correct statement. So model-free means it purely relies on sensing alone. It does not have any models. It does not have any dynamic model that we have already seen. It will only rely on the sensors feedback. It's purely based on sensing. So in that regard, model-free is purely based on feedback. That is a correct statement. Second statement says model-based control are easy to use, but are sluggish and produce poor tracking performance. See, model-based control are basically much more faster than motion-based. It's not sluggish actually, but it has its own limitations. Like if you are using a controller that is purely based on model, if the initial condition of the desired and the actual trajectory are not matching, there will be always an offset. And if there are some external disturbances, the robot will have no means to get back to the desired trajectory also. But again, model-based control are not at all sluggish. It's an attribute of motion-based or sensor-based control. So this is basically an incorrect statement. Option 3 says model-based control are comparatively efficient and simple. That is also correct. But you cannot call it robust. It can be efficient and it can be simple because it might not be very difficult to derive up a dynamic model of a robot. We have seen that in the course. But you cannot call it robust, but it's comparatively efficient, that it's much more faster than motion-based control. The fourth option says the model-based control, accurate model of the robotic system should be available. That is also correct. A model should be as accurate as possible to the actual robotic system. Otherwise, the robot might not be able to track a desired trajectory or a set point, because the controller would depend on the accuracy of the model. And if it is only a model-based control, depending on the accuracy level, it can basically drift away from the desired trajectory. So out of all the 4 options, the only incorrect option is option B. And the question says to identify the incorrect statement. So in that regard, option B is the correct option. See, I am also reproducing the slides from the lectures also. So it basically discusses what a model-based control, the characteristics of motion-based control and model-based control, right? Motion-based or model-free does not have any parameters regarding dynamic model. So it's a pure feedback model. The motion-based is purely feedback or sensing-based. It's easy to use, but it is sluggish, right? And it can also produce poor tracking performance. But in case of model-based control, it can be comparatively efficient and simple. But the limitation would be accurate model should be available. See, like one example is we have already seen this tau would be b of zeta, that is I dot plus n of zeta. If the initial condition of zeta desired at time t equal to 0, time t equal to 0 is not matching to zeta actual at time t equal to 0, from the beginning onwards, there will be some drift error actually. So again, like a lot of limitations are there, we have to make sure that the initial conditions are basically matched, right? So again, that's why they say accurate models. So indeed, the correct answer is option B. The question was to select the incorrect option, and out of all the 4 options, option B was the incorrect statement. Moving on to question 15, it says the necessary conditions for feed forward velocity control to work is. This is basically the feed forward control. And this is the control input. And this is the desired trajectory. Or in case of a set point control, it would not be a function of time, it would be simply eta desired. So what is the necessary condition for a feed forward velocity control to work, right? So imagine what will happen if eta desired dot is 0. If eta desired dot is 0, then this entire term would go to 0, right? That entire term go to 0. We cannot have, we'll always have 0 control in. So so in that regard, eta desired dot cannot be 0, because if it goes to 0, we'll always have 0 control. Okay. Eta desired dot cannot be 0. And another aspect to consider is that eta desired at time t equal to 0 should be equal to eta actual at time t equal to 0. The initial condition of the robot, where the robot is actually starting, it should basically start from the initial position of the desired trajectory. See, if I'll give you more clarity on this. So if this is a desired trajectory, this red line, and if this is the starting point, we would want the robot to start exactly here, so that if you are employing this control law, it will move as per this desired trajectory. If our robot is actually starting somewhere else, it is not coinciding with the initial condition of the desired trajectory, it will still follow somewhat similar to the desired trajectory, given there are no external disturbances or errors. But as you can see, there is a large offset depending on this initial condition. There is a large offset between desired and actual trajectory. This is basically actual. So we have to ensure that in order for the robot to follow the desired trajectory, the initial condition of the desired trajectory and the initial condition of the robot, the actual initial condition of the robot should always be equal or should be matched at the beginning. So in that regard, these 2 options, eta desired at time t equal to 0 should be equal to eta actual or eta at time t equal to 0. And eta desired dot should not be equal to 0. Otherwise, this controller will not work. So in that regard, the correct option is option A. Right? That is the correct option. Yeah. And question 16 says the controller of a land-based autonomic mobile robot is required to have the following error dynamics. This is basically a first order error dynamics actually. Eta tilde dot plus lambda eta tilde equal to 0, where eta tilde would be eta desired. This is a minus actually, not equal to eta desired. Eta tilde would be eta desired minus eta. The question says if the governing equation of the robot in kinematic level is eta dot is j of eta times eta, what should be the control input? Again, like we have already seen this in a previous question. In order for the robot to follow this control law or this error dynamics, if you want the robot to follow this error dynamics such that as time tend to infinity, eta tilde tend to 0, the control input, whatever we are getting as an output of this requirement, is simply the computed velocity control law. And we have already derived that in one of the previous questions. Again, the correct computed as per the computed velocity control law, the correct option would be zeta would be, there will be some feed forward term eta desired dot plus lambda eta tilde lambda eta. And to convert everything back to the body fixed frame, we will also have a j of psi inverse term. So the outcome of this requirement, this is how we want the robot to behave as per the first order aerodynamics. And the outcome of this requirement is the computed velocity control. Computed velocity control law. We have already derived in a previous question. So in that regard, the correct option is option C, I guess. So I think it's option, the second last option, option E. A feed forward term and a feedback term, re-multiplied by the Jacobian inverse. We have already described this the derivation in a previous question, so I hope the justification is clear. So please let me know if I need to further go through the derivation. I'll happily do. Yeah, so going by the solution key, the correct answer is indeed option, the second last option, option E. The question 17, it says in case of a holonomic basis, all the three states xd, yd, and psi cannot be simultaneously controlled. Is it true or is it false? So in kinematics, we have already seen that to correlate the zeta vector, the vector of 2er, to the vector of wheel angular velocities omega1, omega2, omega3, omega4, depending on the number of wheels, we have a wheel configuration matrix. And depending on the rank of this wheel configuration matrix, we can clearly say whether the robot is holonomic or non-holonomic. So if the robot is holonomic, we can basically control all the three degrees of freedom simultaneously, right? Like in case of a mechanism wheel, we have seen that the robot, a mechanism wheel drive, can move in any direction. It can move in lateral direction, it can move in longitudinal direction, it can move about its own axis. It can even move in diagonal ways also. Whatever be the trajectory, it can move in all three coordinates, x, y, and psi. But in case of a non-holonomic robot, such as a differential robot, or a robot like a vehicle or a car like robot, it cannot simultaneously move in all directions. It cannot move simultaneously in all 3 degrees of freedom, xd, yd, and z. It can at most move, like a differential robot can at most have 2 degrees of freedom, and it can at most the controllable degrees of freedom is cannot exceed more than 2, right? So the question says, in case of holonomic mobile basis, all 3 states xd, yd, and psi cannot be controlled. That is basically false, right? We know for sure that for holonomic robots, we can control all 3 states simultaneously. So how do we control non-holonomic robot? If we want this holonomic robot, if we want to move or define a trajectory of a holonomic robot from a starting position to a final position, we can basically either control the position first. It can basically move along this line, right? And once it has reached this final position, then it can basically try and reach the desired orientation. So first we'll make the position error 0, then we'll make the orientation error 0. It cannot happen simultaneously. So that is the drawback of this holonomic robot. First, we have to achieve the position coordinates. After that, we'll achieve the orientation coordinates. So here, like if we align the robot along this line of sight, it can basically move along this line of sight. And once it has reached this final position, it can basically orient about this point to the final orientation, whatever be the final orientation. So in that regard, the correct option is false, because in case of holonomic robots, all 3 states can be simultaneously controlled. And question 18, again, this is also similar to the question that we have seen earlier. This is also a derivation of computer torque control law. We have already derived the computer torque control law. And yeah. And it says, question says the controller of a land-based holonomic mobile robot is required to have the following second-order aerodynamics. We would want the robot to conform according to the second-order dynamics. Eta tilde double dot plus k1 eta tilde plus k2, k1 eta tilde dot plus k2 eta tilde, where k1 and eta tilde is eta desired minus eta. The kinematics and dynamics of the robot are given as follows. So the benefit of following this controller would be that the errors in position eta tilde dot and eta tilde would tend to 0 as time tend to infinity. And we have already derived, if this is our requirement, what would be the control input? Sorry, what would be the control input? We have already derived in a previous question. And as per the previous question, as per the previous derivation, we know for sure that the answer is indeed option A. We have already derived option. Provided this will basically be stable, provided K1 and K2 are basically greater than 0. So that we can have this asymptotic stability. Right? Moving on to question 9, what are the objectives of a control system? So earlier we have come across a question asking a primary objective. Now it says to list out all the objectives. So there could be multiple correct answers for this question. So again, if I'm recalling a slide from one of the introductory lectures on motion control, regarding motion control, and as you can see, the control objectives are basically given as stability. We would want the controller to be stable. As time tends to infinity, the error should always tend to asymptotically tend to 0, irrespective of this initial condition. regulation. Like if we are having an initial position, it should always try to reach the final configuration, irrespective of this initial condition. Trajectory tracking. Trajectory tracking in the sense, yeah, if we want the robot to move such that each and every at each and every point of this time, we would want the robot to follow a particular trajectory or a definitive trajectory. That is also an aim of robot motion control. And optimization, basically. Optimization in the sense like it could mean tuning also, like what could be the ideal control tuning parameters so that the robot would most efficiently and optimally converge to the ideal solution or the desired solution. So in that regard, our control objectives are stability, regulation, trajectory tracking, and optimization. Regulation or set point control, both are basically the same thing. So in that regard, the control objectives are stability. Sizing of the robot does not come under control system. Optimization is also coming under objectives. Signal processing is not there. Sensor processing is also not there. Regulation and tracking are also an objectives of control system. So in that regard, options A, C, and options F, all three options are correct. Right? So options A, C, and option B are all correct. And moving on to question 20. So true or false question. It says the robotic control deals with uncertainties in the given system parameters, and it requires precise knowledge of the structure of the system. We have already seen in an earlier question regarding the definition of robust control and adaptive control. Earlier, we have seen the definition of robust control. And here, this statement, beginning from here, this is basically a definition of adaptive control. We have already seen in the earlier questions. But the question says this is a definition of robust control. But in truth, this is basically, in reality, this is basically a definition of adaptive control. So in that regard, the option is false as well. This is not applicable for robust. This is applicable for adaptive control. Yeah, the option is indeed false. And for question 21, it says finding time history of position, velocity, and acceleration for a set of input joint forces torques is called forward kinematics, forward differential kinematics, forward dynamics, inverse kinematics, inverse differential kinematics. So you are given time history of position. Yeah, sorry. You have theta of t, theta dot of t, and theta double dot of t. And you will obtain a set of input torques as output. So what is this called actually? What is this process called? Is this forward dynamics or inverse dynamics? This is basically, sorry, this is inverse dynamics, right? Whereas in case of forward dynamics, we would supply the control inputs to the robot to see how the robot would move in a space, be it in a task space or in joint space. But here we are giving the robot the trajectory in terms of position, velocity, and acceleration, and to compute the torque that the robot should require to achieve the desired trajectory. So in that regard, the correct answer is inverse dynamics. Inverse dynamics is basically option 21. Yeah. Oh, I think it's forward dynamics actually. Yeah. Okay, I made a mistake actually. It says finding the his time history. I thought it was the other way around. So yeah, finding the time history of position. So we are giving input as torque actually. Time history of torque is given as input to the system, and our requirement is to find the trajectory actually, position, velocity, and accelerations. So like this is exactly what we discussed, but we interpreted the question wrong. So this is basically forward dynamics. Nothing wrong with our concept, but we interpreted the question wrong. So again, finding the time history of position, acceleration, and velocities for a given time history of forces, input joint forces, is basically forward dynamics. But if it is the other way around, if you are giving the trajectory, time history of a trajectory into a robotic system to find out the joint torques, then that would be the inverse dynamics. Question 22, yeah. It says it's a yes or no question, but it's fairly a lengthy question. It says the input affine form. This is basically regarding backstepping or cascaded control. Right. So the essence of the question is the input affine form used for the cascaded control scheme is given as x1 dot is f of x1 plus g of x1 times x2, and x2 dot is f2 of x1 x2 plus g2 of x1 x2 times. And the desired error dynamics is given as E1 dot plus K1 E1 is 0, where E1 is x1 desired minus x1. And E2 dot plus K2 E2 equal to 0, where E2 is difference between x2 desired and x2. The question says, from the perspective of a robotic system, can the state vector x2 be used as a control vector for equation 1? I guess there are no equation 1 here. There is a numbering error. We will consider this as equation 1, 2, 3, and 4. So the question says, from the perspective of a robotic system, can the state vector x2 be used as a control vector for x1 to achieve the error dynamics as per equation 3? Is it yes or is it no? So basically, this is the first subsystem, and this is the second subsystem. This is a general structure of an input affine system. But if we apply in terms of a robotic system, we would know how a robotic system would look like. The kinematics would look something like eta dot would be j of psi times eta, and dynamics would be zeta dot would be d inverse tau minus n. Right? This is exactly similar to this input affine form, where this f1 of x1 is 0, and g1 of x1, this is j of psi, and x2 is zeta, right? And and x2 is zeta, and f2 of x2, x1, x2, from the second equation, from the dynamics equation, is minus d inverse n of zeta, and g2 of x1, x2 would be d inverse, and u would be for the first subsystem, x2 is acts as an input, and for the second subsystem, u is basically the input. So the question says, can we use the state vector x2. Can we use the state vector of subsystem 2 x2 to back to system 1? Can we use this state vector back directly on subsystem 1 so that we can achieve this error dynamics? Right? We want subsystem 1 to behave as per this error dynamics. Is that possible? So this can be fairly straightforwardly answered if you can get the grasp of this cascaded control. Well, we'll see it one by one. So what does this control law states that? The first control law states that. The first error dynamic state that E1 dot plus K1 E1. E1 dot plus K1 E1. This is 0. Where E1 is the difference between x1 desired minus x1. So if I'm substituting this E1 back onto this equation, this prime equation, this would be x1 desired dot minus x1 plus K1 E1 is 0. And if I'm bringing this x1 over to the other side, x1. Right? Sorry, this is x1 dot actually. So from this equation, x1, I'm substituting this x1 dot back onto the equation that we are currently focusing on. So x1 desired dot plus K1 E1 is, if I'm substituting x1 dot, that would be f1 of x1 plus g1 of x1 times x2. And from this expression, what is x2? What is the control input? X2. So on rearranging, this would look something like, this would look something like x1 desired dot plus K1 E1 minus f1 x1, the whole multiplied by g1 x1 plus this would be x2. So I'm copying this thing back to the previous slide. So in order for the first order system, in order for the subsystem 1, in order for the first subsystem to follow this error dynamics, the x2 or the control input x2 should be this, because we have derived it from the backward direction. We have basically derived from this equation. So in order for the subsystem 1 to follow this error dynamics, right, this x2 should be of this expression. But again, there is a conflict of interest because x2 is the state vector of subsystem 2. It cannot be both simultaneously, right? So how the cascaded control law develops further is that from now onwards, we would call this expression as x2d, right? And we would substitute this x2d onto this x2 so that it will satisfy the first order aerodynamics. Now using the second subsystem, we would want this x2 desired using the second subsystem, second error law dynamics, we would ensure x2 desired minus x2 tend to 0 as time tend to. And using the second subsystem, similar to what we did for the first subsystem, we would find out X2 so that this error dynamics can be satisfied. I hope that is clear. I'll repeat this once again. This is subsystem 1. This expression is subsystem 1. This is subsystem 2. And in order for the subsystem 1 to follow this error dynamics, as per question number 3, if we want our requirement is such that we want subsystem 1 to follow this error dynamics, then how would we decide this? How would we design this X2, this control input? It should be as per this expression, right? But this cannot. This should be this expression, but this cannot be simultaneously the control, the state vector of the second subsystem. So this is basically an interim term, basically X2 decide, and using the second subsystem and the second error dynamics, X2 decide this dynamics, we would try to make the difference between X2 decide, this X2 decide and X2. We would try to minimize the difference between this X2 decide and X2 to be more or less equal to 0 using the second subsystem. And similar to how we found this X2 decide, we will again find out the control input X2. So if we again back substitute, our objective of this cascaded control law is to find out this X2. What is this X2 in terms of, yeah, X2, yeah. We would want to find out this X2 so that we would want to find out this X2 so that this error dynamics can be satisfied. So if we substitute the corresponding expressions regarding X2 decide and X2 from these substitutions, we would end up with a value for this control input power. Be some lengthy expression so that the second or this second error dynamics can be satisfied. So I hope you got some idea. So so again, revisiting the question, it says, from the perspective of a robotic system, can the state vector X2 be used as a control vector for equation 1 to achieve the error dynamics as per equation 3? Yeah. Can we directly use this state vector back to subsystem 1 to achieve this error dynamics? That is no for sure, because we know we would want the control input to be this expression so that it can follow the first order error dynamics. So the answer is indeed no. Right? So the answer is indeed no, basically. So yeah, I think we have reached the end of this session for today. This is basically week 7, and next week would be week 8. That will be the final week of this course. We'll discuss some other alternatives for locomotion, some brief overview of other types of locomotions apart from wheel locomotions. Yeah, and I guess that's about it. I think we have reached the time limit as well. So again, thank you all for tuning in for this session. You can always go back to this session will be uploaded in YouTube. Actually, the link will be shared with you quite soon. If you still are not familiar with any of the topics that we have discussed, you can again go back to the recordings of this very session. You can always reach back to me on the discussion forum also. So again, yeah, thanks for joining. If there are no further questions, you can leave. Murali, is there anything you would like to ask? Ah, okay. Yeah, it was a lengthy session. Yeah. Thank you. Okay. Yeah. Thank you. Bye.